5.2. Questions. How is the quantum mechanical model different from the Bohr model? What are orbitals? How does the development of the Bohr model demonstrate the modeling nature of science? Terms. Quantum mechanical model, photon, wave-particle duality, Heisenberg uncertainty principle, orbital, principal quantum number, energy sublevel, spin. Where are the electrons in atoms? 5.2 Quantum mechanical model. Modern physics and the quantum mechanical model. As physicists delved ever deeper into the subatomic structure of matter, it became evident that classical Newtonian mechanics could not describe what they were observing. Gradually, a new theory arose to describe matter on a submicroscopic scale, quantum mechanics. The atomic model that grew out of this new kind of physics came to be known as the quantum mechanical model. It started with a new way of thinking about light. For more than a century, scientists had known that light had properties of a wave. It could be refracted through a lens, and it could be diffracted around a sharp edge. Light also could reflect off a flat surface like a particle. At the beginning of the 20th century, Einstein's theories of matter and energy suggested that light consisted of massless particles called photons. Louis de Broglie. De Broglie's hypothesis. During the 1920s, a young French physicist named Louis de Broglie suggested that if waves could behave like particles, then particles could behave like waves. This concept is known as de Broglie's hypothesis. Whether an object acts as a particle or as a wave depends on how the object is observed. De Broglie's electrons are described as waves that fit around the nucleus when there are whole numbers of waves possible in the distance that they travel. For example, an electron in the second principal energy level is exactly 2 waves long. According to de Broglie's hypothesis, all forms of matter act like waves, including baseballs, pizzas, chemistry students, as well as smaller objects such as electrons and protons. De Broglie waves, or matter waves, increase in wavelength as the object's mass decreases and its speed increases. But such waves are significant only for atomic and subatomic particles. The de Broglie wavelengths of large objects are so small as to be negligible, and the objects appear as particles. On the other hand, for an electron, small whole numbers of de Broglie wavelengths can fit around the circumference of the electron's orbit in Bohr's model of the atom. So, is an electron a particle, or is it a wave? It's both. The electron has a dual nature. It acts as both a particle and a wave, a condition scientists call wave-particle duality. This dual nature explains the movements of electrons that seem to defy the classical laws of motion described by Isaac Newton. Scientists had discovered that light behaves both as a wave left image and as a particle right image. But de Broglie noticed that electrons didn't always act like particles. They can also act like waves. Werner Heisenberg. Uncertainty principle. Scientists were further perplexed when they tried to describe the location of electrons more precisely within the atom. In 1927, Werner Heisenberg determined that it is impossible to know both the energy or momentum and the exact position of an electron at the same time. This concept, known as the Heisenberg uncertainty principle, is a fundamental property of all submicroscopic systems, one that cannot be overcome or avoided. The reason for the uncertainty is due to the limits on our ability to observe atoms because of their extremely small size, smaller than individual waves of visible light. Uncertainty in position times uncertainty in momentum greater than or equal to h divided by 4 pi equals h divided by 2. All information about atomic matter can be obtained only by observing the effects of collisions between the matter and other particles or photons. But the collisions that provide information about matter simultaneously change the phenomenon we are trying to measure. Therefore, the very act of observing properties of subatomic matter changes the properties that we're observing. This aspect of the quantum mechanical model is a good example of the modeling nature of science, as opposed to finding truth. Even with the best and most up-to-date scientific models, there are limits to the extent to which we can know our world. The uncertainty principle gave scientists a new way of describing the regions where electrons are most likely to be found. The regions of highest probability for an electron's location are called orbitals. A diagram that shows these probability clouds, or orbitals, is the modern replacement for Bohr's orbits in the previous model. Each of Bohr's principal energy levels corresponds to a main energy level, and each main level has one most probable position for an electron. An orbital is actually a four-dimensional map because it contains location information in three geometrical directions, x, y, and z, as well as the probability of finding electrons in the time. Orbitals with higher energy predict that the electron's average distance from the nucleus is greater. Electron addresses. As scientists gathered more evidence about the structure of electrons in the atom, they came to realize that every electron has its own energy-determined location within an atom. To identify each electron when the atom is in its ground state, scientists developed an address system that is based on the electron's quantum mechanical properties. This address system uses a series of four numbers called quantum numbers. Quantum numbers are solutions to the various wave equations that scientists use to describe the energy, momentum, and probable location of an electron. For this course, we need only examine a portion of this system. Principal quantum number n. The principal quantum number, n, identifies the principal or main energy level of an electron. In essence, the principal quantum number indicates the average or most likely distance from the nucleus where an electron resides. The numbers are positive integers, beginning at 1, that is, n equals 1, 2, 3, ... 7. The highest value of n for large atoms in the ground state is 7, though it can be much higher in excited atoms. These numbers correspond to the rows, or periods, on the periodic table, which you will learn more about in Chapter 6. All electrons in a given energy level have the same principal quantum number. The number of total electrons allowed in a principal energy level equals 2n squared, where n is the principal quantum number. Sublevels and orbitals. Scientists have developed models that describe the spatial arrangement of electrons. As the models are discussed in the following subsections, you will see the orderly way in which God designed atoms. These theoretical models have been extensively confirmed by analysis of emission spectra and other kinds of tests. Unlike the Bohr model, the quantum mechanical model subdivides all but the first principal energy level into energy sublevels, or energy subshells. These sublevels are further subdivided into orbitals, each of which may contain up to 2 electrons. The 4 energy sublevels have been assigned the letters S, P, D, and F, respectively, to avoid confusion when describing an atom's electron structure as it relates to chemical behavior. Because quantum theory predicts where an electron is most likely to be found, it is most accurate to call an illustration of a sublevel a probability plot. The S sublevel. The S sublevel is the simplest of all. A probability plot of an S sublevel has a spherical shape. Unlike the other sublevels, it contains only one orbital, so the orbital is often called the S orbital as well. Every principal energy level has an S sublevel that contains one S orbital. Remember that an orbital can hold a maximum of 2 electrons, though it may contain fewer. Each of the 2 possible electrons in a sublevel has an opposite spin, a form of angular momentum carried by electrons, the p sublevel. The 3 dumbbell-shaped orbitals of a p sublevel probability plot are arranged symmetrically around the origin of a 3-dimensional XYZ graph. One lies on the x-axis, one on the y-axis, and one on the z-axis. Because of this, p orbitals are sometimes designated px, py, and pz. There are no p orbitals in the first principal energy level since it has only one s sublevel. Every neutral atom in its ground state with 2 or more principal energy levels has a p sublevel. Since each orbital can hold a maximum of 2 electrons, a p sublevel can hold a maximum of 6 electrons. The d sublevel. A d sublevel probability plot has a more complicated shape. The 5 orbitals in the d sublevel are oriented as shown at left. Atoms in their ground state containing 3 or more principal energy levels may have d sublevels. A d sublevel may contain up to 10 electrons. Image showing 5d orbitals, dxy, dxz, dyz, dx squared minus y squared, and dz squared. The F sublevel. An F sublevel probability plot is even more complicated than the d sublevel plot. The figure below shows the 7 possible F orbitals. Only ground state atoms with 4 or more principal energy levels may have an F sublevel. An F sublevel may contain up to 14 electrons. Putting them all together, you may have noticed that some orbitals overlap one another. The overlap teaches they are probability regions for the locations of electrons, regions where electrons might be found, not definite locations. When all of the orbitals for an atom are combined, a roughly spherical region is produced around the atom called the electron cloud. This cloud contains all the electrons of the atom and extends into space. You may also have noticed that there are potentially a lot of principal energy levels and sublevels to be found in atoms. The sublevel being discussed by combining the principal quantum number and the energy level with the letter is the standard way scientists label them, such as the 3p sublevel or the 4d sublevel. An electron in one of the 3 orbitals of the level 3p sublevel will be used later in discussion. Electron capacities. There are limits on the number of electrons that can occupy the various principal energy levels, sublevels, and orbitals of the quantum mechanical atom. The first energy level of any atom contains one s sublevel with only one orbital, which can hold 2 electrons. Thus, the total capacity of any first principal energy level is 2 electrons. Each second energy level has one s and one p sublevel. Since every p sublevel has 3 orbitals that can hold a combined maximum of 6 electrons, the total capacity of the second principal energy level is the sum of the 2 electrons from the s sublevel and the 6 electrons from the p sublevel, a total of 8 electrons. The total capacities of the other principal energy levels can be determined by a similar procedure. Table 5-1 lists the total allowed electrons in each of the 7 ground state principal energy levels, relative energies of sublevels. In Bohr's model, as the energy level of an electron increases, the distance of the electron from the nucleus increases. In the quantum mechanical model, this simpler view was replaced by a more complex relationship. Principal energy levels become larger in size as their energy level number increases, but their sublevels are also ranked by their relative energies. Beginning with the innermost energy level, the 1s sublevel has the least energy. The probability plot for the 1s orbital is the closest to the nucleus of any orbital. The 2s and 2p sublevels in the second principal energy level have more energy. They are farther from the nucleus. Note that all 3 2p orbitals have the same relative energy, and the electrons in these orbitals have more energy than those in the 2s sublevel. Farther out and higher in energy are the 3s and 3p sublevels. When you consider Table 5-1, you might expect that the next higher energy sublevel after 3s and 3p should be 3d. However, as the number of electrons in an atom increases, their interactions become increasingly complex. As a result, the next energy sublevel to be filled in a ground state atom is actually 4s. In Section 5.3, you will learn how the periodic table reflects this filling order, but there is also a simple diagram that can help you. The figure at right is sometimes called the diagonal rule because the parallel diagonal lines help you remember the filling order. If you start with the top arrow and work your way down, you can see the order in which the sublevels fill.